is Wake Forest University?
Wake Forest is in North Carolina, so it's about an hour west of the Research Triangle where we do chapter.
Jason is in our program, as you know, so there will be plenty of time to ask you questions, extended questions, at any time later on. Meanwhile, he will tell us about Helicity cosmology, no, cohomology. It's just wishful thinking.
Yeah, that would be great, but I'm afraid I have little to say.
Configuration space.
Well, thank you, Conrad, and thank you to the Isaac Newton Institute in general. This has been a wonderful place to come work, and many wonderful people to talk to. So today I'm going to tell you about a view of helicity that Jason Canarella and I came up with using cohomology and configuration spaces. And I'll try to tell you why this is a useful framework to view helicity, as well as give you some applications of things we can do with it that are quite nice. And also, I'll talk about this goal. Well, this is the goal for today. To show that we can recognize helicity using some algebraic topology structure and view it as a cup product via cohomology. And I stole a couple of Jason's slides on a background in cohomology. I'm sure I see several experts in topology here, so for those of you who aren't, I'll give a gentle introduction.
Very dynamicist.
And in some ways, this is really that's really the target audience. The people I'd like to reach is to say, hey, here's a reason why we can do this with homology, and a pervading goal that Clay talked about, and I know many other people have thought about, is can we find other invariants like helicity? And so at the end of my talk, I'll say some things about that, both obstructions and encouragements. So some background. We want to think about diffeomorphisms of a domain in 3 space or in 2k plus 1 dimensions. If this scares you, thinking about higher dimensions, just let k equal 1 and think of 3 dimensions. But a diffeomorphism represents how a domain may change under a nice way. In particular, S-diff will represent the diffeomorphisms homotopic to the identity, that is, that you can get by a true deformation of the domain and get back. So helicity has been known for a while to be an S-diff invariant, and this question that we'll get to at the end, are there other S-diff invariants? Gee, it sure would be nice to find other S-diff invariants and then go and understand all of their physical meaning. But instead, we'll talk about certain obstructions as well as what we gain by this. So there's a big question that a number of people have thought about. So which diffeomorphisms will helicity remain invariant under? And I guess I've only put a couple groups that have results here. So Vladimir Arnold and Canarella, de Tuckler, Gluck, and Teitel. Together, if you combine their results, helicities of a vector field is invariant under any volume-preserving element of S-diff. So that means you take your domain, you let a magnetic field flow along it for a while. The domain may change slightly, but if it's doing so in a nice S-diff way, helicity hasn't changed. And so already we see the physical intuition coming in there. If the domain is simply connected, so it's like a ball, or the vector field is fluxless, so across a nice cross-sectional disk, the field has 0 flux, then you can drop the S part of this. You no longer need to worry about diffeomorphisms that are homeomorphic to the identity, and for a vector field, we do require that it's volume preserving. So another question, one that we'll be able to give some answer to, is do other helicity preserving diffeomorphisms exist? Now, let's take a quick look at cohomology. And so I should say that for those of you that were in Edinburgh and went to Jason Canarella's talk, we're talking about the same results. And so this may be take 2 for some of you. Others in the audience have heard me speak on this before, and so it may be take 5 or 6. And but I know not everyone was in Edinburgh, and so I wanted to run through all of the material. I will have a chance to say some things that Jason didn't up at the ICMS workshop. So physically, let's say we have a curl-free field. Is it a gradient? And I mean an honest-to-goodness gradient, a single-valued function here. I'm a mathematician. I don't deal with gradients of multi-valued functions. I recognize those as a gradient of a single-valued function plus a period. So periods. Cohomology tells you that the answer depends on the periods of the field. That's really one way to think about first cohomology. Well, let's measure the period of the field around a loop. For a double torus, you've got a dimension 2 set of loops to consider. And if you know the answer on a basis for them, you know the answer in general. One could also view relative cohomology, which is a way of measuring quantities like this relative to the boundary. So instead of taking a loop here, we might take a disk that has its boundary on the boundary of this solid double torus. And so in the analogous sense to these loops, and to answer this question up here, one would want to consider these surfaces and examine the flux over them. And so relative cohomology is a way of keeping track of fluxes for differential forms. And basically, the answer to this question is that, well, if there are no non-trivial periods, well, the answer is yes. If there are no non-trivial fluxes, the answer is yes. But for a solid double torus or a solid torus or anything with non-trivial first cohomology, this isn't always the case. It isn't always true that a curl-free field is the gradient of a field. Okay, so next let's talk about how to combine cohomology and relative cohomology. If one thinks about it long enough, or just simply stares at this picture, these are dual notions, right? Every period here went through one and only one of my flux spanning surfaces, and we'll talk about this more later, but you can always choose a basis for cohomology and relative cohomology so that that's the case. If you do this by Poincare duality, you can, then there's this idea of a cup product in algebraic topology which pairs periods and fluxes, cohomology and relative cohomology, and it's nothing more than the wedge product of differential forms. We'll be able to use this and recognize helicity as a cup product. So, linking. This is something that maybe the audience shares a great affinity for. The linking number of two curves is that can be determined in several ways. One of the nicest, the one that fits with the framework of my talk today, is to view it topologically as the degree of a map from one curve across another curve, where we take this Gauss map into the two-sphere by picking a point x and a point y on the two curves respectively, and normalizing the vector in between them. So that is, take x minus y over its norm, and you get a point on the two-sphere. And what Gauss undoubtedly realized was that you could use this to make an integral formula. And so if you take the area form, normalized to have unit area 1 over here, and pull it back, that's precisely how you get a formulation of the linking integral. And the reason this works is that S1 cross S1 has cohomology in dimension 2. You're picking something up there. Gauss did come up with this formula here, and we may know it well because it mimics helicity, or helicity mimics linking of curves. You can view helicity as the average linking number of flow lines in the domain. And what we'd like to do today is recognize helicity in terms of an algebraic topology framework similar to the degree of the map that we saw for linking number. However, and this is a big issue if you start thinking about it, if you take a nice simply connected domain omega, like take a ball, a solid ball, cross it with itself, well that doesn't have any cohomology in dimension 2. So where are we going to pick up something that's going to tell us about helicity? So let me tell you what I'm going to tell you for the rest of the hour, and that's the following. So first, I want to switch to the language of differential forms, and I'll remind everybody what a differential, or how we get a differential form out of a vector field. It's worth saying that everything we've done actually extends to forms in 2k plus 1 dimensions. These are no longer forms related to vector fields per se, but they're related to kind of products of vector fields. And so one of my questions is, well, are there any other situations where k plus 1 forms are useful? We'll go through configuration spaces, which I know Clay introduced at his talk a few weeks ago. We'll talk about a few different ways to look at helicity. We'll show S-diff invariance and get it almost for free. We'll talk, as I said, about the change of helicity under arbitrary diffeomorphisms and find a nice formula to express that. So we'll mention some other diffeos that do preserve helicity, talk through some applications, and then at the end, why can't we generalize helicity very easily? Okay, so now what's a differential form? Well, it inputs two vectors, at least a two form does, and outputs a number. You can get one by, from any vector field, you can make a two form by just taking the volume spanned by these three vectors. A divergence-free vector, which is tangent to the boundary of a field, so that is modeling a frozen-in, steady magnetic field. This can be re-expressed in the language of differential forms as a closed two form that vanishes on the boundary. So we use Dirichlet as the name to talk about that. So a closed Dirichlet two form. And one nice result that's true in Euclidean space, if you have a top dimensional subdomain, like solid torus sitting in R3, every closed Dirichlet form is exact, meaning it does come from a gradient, if you will. It does have a primitive, I'll say it that way. Strike the gradient comment. So our alpha up here represents a relative cohomology class, but omega may not have cohomology. Again, we're back to the question, where is this cohomology class coming from? And it comes out of configuration spaces. So configuration spaces will also let us bypass the following issue in the helicity integral. One of the first things I encountered as a grad student looking at helicity was that, well, this integral's improper. It's not well defined where 2 points have come together. And it wasn't a hard exercise to go through and show that this integral still converged, that this was okay, the singularity was not bothersome. But it was something to do, and in essence, it meant we weren't really integrating over the whole space here. We were throwing out the points where x and y had come together. So if you take n distinct points on a space x, put them in order. So you've got an n tuple of distinct points. The space of those points is known as the configuration space Cn of x. For instance, if you have a nice subdomain in 3 space, this really is omega cross omega minus the diagonal of points where x and y have come together. The issue, if you want to start integrating things, is we always integrate over compact regions. C2 of omega is no longer compact. We threw out a lower dimensional set here. It's open as we approach the boundary. And there's a nice way it turns out, to recompactify it. You wouldn't want to throw the diagonal back in, because then you just get back to omega cross omega, which is the space we started on. Didn't have cohomology, didn't have a proper integral. So we compactify using the Fulton-McPherson method to what I've written as C2 bracket omega. This means take the diagonal and replace it by the unit normal bundle. That is, record the direction of approach of points that come together. So if x and y are coming together, I want to record how they did so. I no longer want to keep that diagonal in my space, but by doing this, you get a well-defined space C2 omega, or in general Cn of an arbitrary space x, and C2 omega is going to have a new cohomology class in it, which it's going to be non-trivial even if omega is as nice as it can be. So I'll do an example of that to start with, or in a second. But to start with, let me look at just a couple easy examples. C2 of the interval 0 to 1. So we take 0 to 1 and cross it with itself. We get a square. We throw out this diagonal. So what I'm doing to make this space is now replacing this diagonal by its unit normal bundle, which is, well, this is too trivial of an example because the unit normal bundle is just 2 copies of the diagonal. And the point I wanted to make here, though, is that this splits the square into 2 separate pieces. There's now 2 disconnected components. The same thing happens, and this is a fun example to work through. If you take 3 points on a circle, C3 of S1 breaks into 2 solid tori. One reason to see that this has to be a disconnected space is, imagine we take a circle and now simply put 3 points on it, 1, 2, and 3. You have either put them in a clockwise fashion or a counterclockwise fashion. And depending on which way you did, you may then rotate your points in any way you like to get from one clockwise position to any clockwise position. If you have 1, 2, and 3 going around clockwise, you can move them kind of like balls on a circular wire. But you'll never be able to make them look like 1, 3, 2. And so that's an important point. This configuration space will definitely inherit the topological features of X, but it will have extra structure, and that extra structure is important for us. So now let's look at a disk, and let's just do it, well, I wrote the slide in 2k plus 1 dimensions, but again, it's always fair to replace k by 1 and think of just a 3-dimensional ball. So omega cross omega is a 6-dimensional space. It's homeomorphic to a 6-dimensional ball. And if you throw out the diagonal, that's really like throwing out 1 point in the second ball. You could think of it as a ball crossed a ball with the, where we picked the point x here, and we've removed it from the second ball. And, well, that ball is really, can be deformed to, so that the point that's missing is at the origin. So that means it really looks like a spherical shell, a sphere across an interval. But we could throw this interval onto the disk and get something that's homotopic to a 4-dimensional ball cross a 2-sphere. Aha! This 2-sphere is where we're getting the 2-dimensional cohomology from. And by Poincare duality, you know that the 4-dimensional relative guys that we're picking up, so that is that have boundary living in the boundary of C2 omega, like D4 would, well, they're isomorphic as a group to the 2K ones, or for us, K's 1, so the 2-sphere here. These both have cohomology groups that are just equal to R. They're the same. They give us the nice cup product structure. So having said that about the topology of configuration spaces, let me now try to begin constructing Helicity. Okay, so here we go. We'll start with our vector field, B. may prefer to call it B, magnetic field, divergence free tangent to the boundary. Make the corresponding two form, so it's closed Dirichlet in our language. And consider this projection map where we just think of C2 omega. Well, away from the boundaries, this looks like two copies of omega. So just project onto the first copy. You've got to take care near the boundary to understand what this map looks like. But in spirit, that's what's going on. You can pull back your form alpha that lives over here to this larger space via this map and make a form alpha x that in spirit really is just a copy of alpha. Same thing for alpha y. If you take their wedge product, it is both closed and Dirichlet. It vanishes on the boundary. That means it represents in this relative four-dimensional cohomology. To say a bit about the proof, well, when you pull back a closed form, you get a closed form. So number 2 is, or number 1 is trivial. After an understanding of differential forms, you wedge two closed forms and you get number 2 to fall out. 3 takes some work. We actually did a computation in coordinates to show this, and it took getting our hands dirty with configuration spaces. And so that's really the statement of the lemma, is that 3 holds. Now we can define helicity. We can do it for k+1 forms on a larger dimensional space, but let's still think of 2 forms that come out of a vector field on a 3-dimensional domain. Consider this Gauss map again. xy goes to x minus y over its norm. We're mapping into a 2-sphere. The 2-sphere has an absolute 2 cohomology class. We're going to pair that with our 4-dimensional relative class and use the cup product structure. So the first lemma we had to prove was that G is a smooth map defined on all points of the configuration space. This is certainly true away from the boundaries where the configuration space just locally looks like omega cross omega. On the boundary, remember how we compactified. We threw out the diagonal, but we kept track of the rate or the way the points came together, the direction in which they merged. Well, that's precisely what the Gauss map wants. What is the direction between the points? So that's why we will get this extension back to all of C2 omega with the Gauss map. And pulling back the area form on the 2-sphere gives us a closed 2K form. It gives us that absolute cohomology class. And after you have both of those, you can't help but use the cup product structure. Here's my 4-dimensional relative cohomology class. It's a relative cohomology class because it's a closed Dirichlet form. That was the lemma on the preceding slide. Here's our 2-dimensional pullback of the area form, absolute class, so relative cup absolute. That gives me a multiple of the top dimensional volume form on C2 omega. What multiple? The helicity. It couldn't be anything else. Because after all, we're integrating something here that in spirit is v of x cross v of y dotted with x minus y over its length. There's a normalization factor in there, an inverse square law showing up. But this really is the standard helicity integral, at least written out with the Biot-Savart law to find the vector potential. So if you preferred to see B wedge A, this part would be A.
That's not the union sign, it's something else.
Yeah, that's a good question, Asher. So this is a cup product sign. And probably if you have good typesetting, it is slightly different than a union sign, but I always have to convince myself when I'm reading. But here, this means cup product. So we're taking a 4-dimensional relative class and a 2-dimensional absolute class. That gives us a 6-dimensional absolute class, which, so it has to be a multiple of what measures the volume. So, why is this important? Well, we get invariance almost for free now. This is topological. The cup product structure is unchanged by diffeomorphisms. So that means when you calculate this cup product, you're going to get the same number out, no matter how many diffeomorphisms homotopic to the identity you've done. So we have our S-diff invariance. I remember when I first, as an exercise, as a grad student, proved that Helicity was invariant under diffeomorphisms that were volume preserving and homotopic to the identity. It was a nice computation to go through material derivatives and some other things, but it definitely was some work and analysis to do so. Here, topology saves us from that work. Okay, now I really do want to break away from 3 dimensions and talk about why Helicity will work in 3 dimensions, in 7 dimensions, in 11 dimensions. And it gives us an invariant in 5 dimensions, in 9 dimensions, in 13. But unfortunately, that invariant is just always 0. It's a trivial invariant. And I think Bott knew this, among lots of other people. But let's show this result. In other words, Helicity only works for dimensions that are 3 mod 4. And if we look up in this integral and interchange x and y, we will reverse the orientation of the configuration space. We will swap these 2 forms, and in the language of forms, when you swap them, you introduce a -1 to the power of the form. So here it's a k form, so we get a -1 to the k. And so our overall change is -1 to the k plus 1. So if k is even, Helicity is trivial. But k being even is precisely when we get 4i plus 1. K odd gives us 4i plus 3. Now let's take a sojourn into knot theory. So Bott and Taubes came up with a way of computing the Vassiliev invariance of knots. A Vassiliev invariant can also be called a finite type invariant, and we could spend a lot of enjoyable time going through what these are, but let's just call them certain knot invariants for now, where you can take the space of all knots and cross it with the configuration space of endpoints on the circle. I want n to be even here. And that's because I want to take a Gauss map into a product of 2 spheres. So if I had 4 points, maybe I'd want to pair the first and third together and map them to one 2-sphere, and pair the second and fourth together and map them to another 2-sphere. If you pull back the volume form and then integrate it against this space, you'll get a function out that lives on the space of knots. And if, after doing this integral, you get something closed, meaning its derivative is 0, well, my calculus students can tell you that means it's locally constant. So it's constant on the connected components of the knot, this knot space, which are exactly the isotopy classes of knots. So in other words, you get something that's a knot invariant that won't change under isotopy of knots. Let's actually do an example of this, and we'll mention this as maybe the second to last slide today. I've got many more to go, but we'll see this coming up at the end. So here's an x integral where we do pair points as I just described. 1 and 3 go together, 2 and 4 go together, and we pull back. This notation means take a Gauss map using the first and third guys, use the second and fourth guys, and pull them back, or pull back the area form on the 2-sphere via them. If you go through and compute the differential of this integral, so take d of this integral, you have to look at boundary terms, and you get something that's not 0. So it's not closed. But that goes against what I just said on the previous slide, because if you got something that was closed, that's where you got, a function that was locally constant. Well, Bott and Taubes were smart enough to figure out that you could cancel out this effect of the x integral by taking a slight modification of it and pushing a 4th point to lie anywhere in space. So we call that y to signify that it's different than the 3 x points. And there's this notation for doing so. You now have 3 different Gauss maps, y connecting to each of the 3 points. And if you choose a suitable constant for to multiply the y integral by, you now can take the difference of ix minus iy and get something that is closed, that is locally constant. So you get knot invariants. And these are, this one is specifically the Vasiliev type 2 invariant, which is the second coefficient of the Conway polynomial. So this has a lot of utility. And we did this same construction for vector fields. So for us, let's look at the space E of all embeddings of our domain into 3 space. If you really want, into 2k plus 1 space for a higher dimensional domain. And we can then take a Gauss map into S2. We can pull back the area form. The wrinkle here is we're not just going to take that form, but we're going to wedge it by our 4-dimensional relative cohomology class here, 2 copies of the vector field turned into a differential form. So we make this 6-dimensional form, alpha x wedge, alpha y wedge, pullback of the area form, and we integrate it against the 6-dimensional space C2 of omega. We get out something that's a function on the space of embeddings. Which function is it? Helicity. So helicity is a 0 form, i.e. a function on the space of embeddings. D helicity, you can do this computation, and you get 0. It's a locally constant function on this space. Well, what are the connected components of the space of all embeddings? They're precisely the diffeomorphisms that are homotopic to each other. So we get helicity to be a function that's constant on the connected components of embed, i.e. on homotopy classes of diffeos. The last thing we did, and this turns out to be useful, but more of an exercise to just make sure everything with forms was working the way we wanted, was to define a Biot-Savart operator to get a primitive of a form. So if we wanted to calculate a primitive of alpha, you could do it in just the way that you might use the Biot-Savart law to calculate a vector potential or so forth. So you take alpha y wedge the pullback of the area form and integrate it now over the C21 omega, which is really kind of like a copy of omega sitting in C2 omega. If you start with a closed Dirichlet form, then you do get a primitive of alpha with Bs of alpha, i.e. taking its differential returns you to alpha. And then you can recover the maybe shortest formula for helicity, that helicity is A wedge B, except kind of counterintuitively, this would be the A and this would be the B. But you get the standard way of looking at helicity. Why do we want to do that? Well, it allows us to approach this question. Earlier in the talk, I mentioned that while helicity was invariant under a lot of different types of diffeomorphisms, subject to hypotheses on the domain or the diffeomorphism, what about in general? So what Canarella and I were able to do was measure the change of helicity under a diffeomorphism. So if you take an orientation-preserving diffeomorphism at least, then define the pullback of our form that lives here, S alpha prime over here. So it's going to push forward naturally. And we might want to say, what's the difference between helicity of the form here and helicity of the form here? We've got some results from Arnold and from others on when this has to be 0, but what is it in general? And the wrinkle is, well, here was our formula for calculating helicity. If you take the helicity of alpha prime and change coordinates back to the original space omega, well, alpha prime just pulls back to alpha, This does not pull back to BS of alpha necessarily. It pulls back to this other guy, which is, kind of convolving it by the action of F, if you want to think of it that way. F star BS of pullback alpha. F star BS of alpha prime. These two red guys are not equal, but they are both primitives for alpha. And because of that, we can actually calculate the change of helicity. So let's write this difference. That's the difference of the two primitives. I'll denote them beta tilde and beta just for simplification. You can do a little bit of calculus and show that, well, this reduces to a boundary integral. If k is odd, it's a pretty simple one. It turns out to just have a cup product structure again. See a prevailing theme through this talk? If it's even, remember this was the case where helicity was a invariant that was always 0. So we can basically throw this case out. And you can begin to see why that's true also over here. But let's focus on this case. And this really is now a two-dimensional integral. And these are both one forms. So we have another cup product structure of the cohomology classes for beta and beta tilde. We'd like to now understand this cup product, but we need some topology facts about three-dimensional domains and their boundaries. In particular, the homology or cohomology of the boundary splits up into the homology of what's inside and the homology of its complement. And rather than go through that, it might be easier for me to just show this picture. You can kind of tell who made which pictures in this presentation. Mine are usually hand-drawn and messy, but colorful. And Cantarella's pictures are always fantastically beautiful and computer-drawn. So this is one of mine. And so take two curves, S's, that give us periods. So these are going to be in our homology class. If you take the periods, they'll be our cohomology generators. This is a solid double torus. So its first cohomology class has dimension 2. And each of these spans a surface that lives outside of the region. If you took the relative cohomology surfaces that live inside of here, they are bounded by curves T1 and T2. And these curves actually represent absolute cohomology classes, or homology classes, in the complement of omega. And the nice thing is you can do this anytime you have a Euclidean subdomain. The boundary homology splits into the boundary, the homology of the region and the homology of the complement, and they're a direct sum. So on the boundary, we actually have 4 different loops that we could draw in first homology, the 2 S's and the 2 T's. And we know that the blue S's are kind of dual to the tau's, but the tau's are in accordance with the red T's. You can set this up so that the cup product structure is particularly nice, so that the only thing that survives is Ti cup Si. In general, you'd have to worry about Ti cup Tj, Si cup Sj, Ti cup Sj, and so here you just need to pick the right basis. So if you have a diffeomorphism F, what that's going to do to one of the SIs is send it to SI primes, the similar guys sitting over in the new copy, omega prime, plus possibly some Ti terms. You can't be guaranteed that your diffeomorphism is just going to send SIs to SIs. You can make it so that TIs always go to TIs. And so on the language of matrices, this is saying the SIs map to only an SI, no SJ terms come up. The TIs go only to TI primes, SIs go to SI primes. The TIs go to no SIs, but the SIs go to some TI primes. And I've got a pic, if that's confusing, I've got a picture coming up. Each of these represents a D by D matrix, where D is the dimension of the kth homology group, and this matrix can be chosen as symmetric. With that construction, here's how helicity changes. The difference between the new form and the old form is, well, you take each of the coefficients of this matrix and you multiply it by the appropriate two flux quantities, flux of, across the ith surface and the jth surface. You sum that up over all entries here. That's the change of helicity. Okay, so here's an example of what's going on here. This is a picture Cantarella drew of similar double torus. But let's say we wanted to take our diffeomorphism F that's going to do a Dane twist here. So this is going to take S1, and map it to this S1 prime that loops around here 3 times. And it goes around the neck of this double torus once. S2 gets mapped to this curve that goes around this neck once. And so the map in terms ofCij's is that, well, S1 became S1 prime that now goes around the short way once, the long way once, and the short way 3 times over here on the left. S2 went to S2 prime, which goes along the long way once. Both TIs went to just TI prime. And that's how we get this matrix coming out. So if you wanted to then plug that into our formula, the difference in helicities would be, well, the only term that survived was the 1,1 term. So you would have 3 times the flux of alpha over the first surface squared. In the interest of time, because I want to talk about some applications here, I'm going to skip the proof of this and only just mention that we calculate periods of alpha, or of this primitive over these homology loops, over Ti and Si. And because it's a primitive for alpha, we can make these into flux integrals, and that's how the flux terms show up, and then the cut product structure gives it to us. And sorry to rush that, I'll be happy to talk later about that. But let me instead talk about an example. So if we take a Dane twist on a torus, so we make these horizontal fields turn into 1,1 curves on the torus, you can compute the helicity of the original guy. These are just planar field lines. It has to be 0. They don't link together. These give you pi squared r to the 4th, where r is the inner radius of the torus. For us, we're mapping our block matrices are mapping a one-dimensional space to a one-dimensional space. So you can just write it as a constant, and the constant is 1. So the change in helicity should be 1 times the flux across the spanning disk squared. Well, the flux for a unit vector field here is pi squared, or pi r squared. You square that and you get the computed helicity. Why might this be important? Well, okay, this is a very perhaps non-physical way of a magnetic field evolving. And I can think of 2 potential uses for this. One is maybe there's some sort of dislodging and reconnection of the tube that actually does institute a twist like this, a Dane twist. And you may want to measure helicity after this reconnection of sorts. Another might be, say you want to view your field this way, but you want to compute in these coordinates. Well, maybe you can do that, and the price you'll have to pay is just, if you're working with helicity, prescribed to you. Here's an example of something that is helicity preserving, but not an S-diff. take a Dane twist around this curve. That gives you an identity map on the homology. So Cij is an all-zero matrix. That means the change in helicity is 0. This is not a map in SDiff, but it is helicity preserving. Let's see. So now I wanted to talk about one application, and then at the end I wanted to talk about obstructions for other helicity invariants. So we had our cohomology class way of looking at helicity. Take a 4-form that represents a relative dimensional cohomology class. Take an absolute 2 class and take their cut product. Well, what this says is we could take any volume over here, or any form on the 2-sphere that's cohomologous to our standard area form. And the easy way to calculate linking number for knots motivates this. So the easy way to do linking number for knots is to just look at a projection and compute the sign of each crossing. That is, look at where one strand is over another strand. If you think of this distance as being vertical, what this is kind of doing in the Gauss integral framework is concentrating area around the north pole of the sphere. So you could write Gauss's formula picking a different area form on the 2-sphere that just is mostly measuring around the north pole, and get an equivalently good notion. Concentrating all of the area at the North Pole is precisely reducing Gauss's formula to the sign crossing number formula. We can do this for helicity. So what it looks like, let's see, wrong button here, is we're going to want to still take 2 copies of our vector field, and instead of dotting them with the vector from x to y here, dot it with a vertical vector. What changes is we don't integrate over omega cross omega or C2 omega anymore. We only integrate over the y points that happen to lie immediately over the x point in consideration. And I'll skip the proof in the interest of time, but I'd rather talk about the example. So if you take 2 linked tubes, and these tubes don't have circular cross-sections. They have, say, rectangular cross-sections. By results of Keith and Berger and Field, you know the helicity has to be the helicity of the vector field in the first guy plus the helicity of the guy in the second, of the field in the second tube, plus the linking number of the 2 tubes, in this case 1, times the 2 fluxes. Well, for us, this means you could actually calculate the helicity by only looking at points in the second tube that lie directly above points in the first tube. So for most of the volume of this tube, you no longer have to worry about it. Instead, we only need to look at kind of this parallelogram over here, where the second tube is above the first tube. And if you go through and actually figure out what's going on there, you get something like a sine theta term coming in with the for measuring the area of the parallelogram. You get a W over sine theta term, and so our volume of integration is W squared H squared over sine theta, and it gives you the correct result for helicity. You get W squared H squared, which is exactly what the Moffat and Berger and Field results suggest. Okay. So the 2 big applications I'll point to out of our cohomology work are, 1, we get to compute the change in helicity under an arbitrary diffeomorphism. And 2, we get to sit around and propose different integral formulas for helicity, like this one. How useful these formulas may be, well, I don't know. I mean, perhaps if you're doing numerical simulations, reducing things from a 6-dimensional domain down to a 4-dimensional domain can really help. but perhaps not. Now I want to talk about, can you generalize helicity? Are there other diffeomorphism vector field invariants out there? And to get started here, we could view helicity as kind of a 4D flux. We've taken 2 copies of the vector field. And here's our one quick conclusion we can come to. If you take any integral that looks like helicity, where you start with v of x across v of y, and then dot it with some other term, you're taking a triple product. If w is x minus y over that norm cubed, you get helicity. And if you pick any curl-free field here, the only thing you could get out that's non-zero is helicity, or some multiple of it. The reason? There's only one non-trivial period in this configuration space, one non-trivial flux. We're only getting that one non-trivial two-dimensional cohomology class. I'm assuming here that we're talking about a 3-dimensional ball. If you have something as your domain that has more topology inherent in it, then you may be able to get other things. And that's what I'll talk about in future slides. So let's see if we could find an S-diff invariant that works on arbitrary domains. So in particular, it has to work on the ball. That means something like this won't do it. Well, when I think when Cantarella and I first started thinking about this 7, 8 years ago, we were really motivated in trying to find other configuration space approaches to helicities. Trying to find other invariants via these configuration spaces. You can certainly construct a 2n form on the configuration space of endpoints on a ball by taking alpha n times. You've got n copies of your vector field or form. Could you possibly pair that in the right way with an n-form beta and get something useful out of it? The answer is no. And any integral invariant you write this way, n copies of alpha wedge beta, where beta is some closed n form, it again has the same result as the previous conclusion. It's either 0 or it's helicity in disguise. Maybe it's helicity squared. Maybe it's a constant times helicity squared. But that's the only thing you can do. Why? Well, computing the cohomology of this space, once you have endpoints on it, that's a much more difficult prospect than computing it when you can only take 2 points. However, Fred Cohen has done this, and he's shown that it's generated by cup products of 2-dimensional classes corresponding to pairwise Gauss maps. Meaning, you could say, well, I've got endpoints, and maybe the only good 2 class I could pick up here is one that maybe takes 1 and 3 and puts them together, and 2 and 4 and puts them together. Well, if I do that, and I have 4 copies of alpha, all I've really done is written down helicity times helicity. So I'd get helicity squared out. If you try any other form beta, you're not going to get something that properly represents in cohomology. Your cup product structure is doomed to fail. That means you just aren't going to be able to mimic this cup product construction and get out an invariant. No. This is kind of a weaker version of what Bader and Marché said 4 years ago. They said if you take a vector field, V, ergodic, that does not charge any periodic orbit. One way to think about this is it does not flow along any homology loops, at least with non-zero flux. If you take any Vasiliev invariant of knots and in Arnold style flow along it for a while, then close up the flow line by a straight line, so this short curves approach of Arnold. If you then take a limit as t goes to infinity, the only thing you'll ever get out of a Vasiliev invariant is a constant times the power of helicity. In other words, this Vasiliev invariant, this Bott-Taubes approach, this configuration space approach, it's not going to give us global vector field invariants, at least the way we're currently thinking of it.
It's a constant in what sense?
Lambda is just a real number, so a true constant that you may say if you took
It's constant with respect to what kind
Constant under
what
diffeomorphism.
changes.
constant under diffeomorphism. So if you were trying to deform the domain under an S-diff action, so a diffeomorphism homotopic to the identity, then the only thing you could get out is a constant times helicity. It is true, of course, that if you started taking different domains, you could recover different constants. Does that answer your question, Conrad?
Probably.
Yeah, this is a diffeomorphism invariant.
My problem was that if you have two numbers, they are always related by a multiplicative constant.
Oh, sure.
But is it constant of?
Yeah, so it will change as we change the Vasiliev invariant. So will this power n. But if you were to pick a different flow line, you'll and the same Vasiliev invariant, you'll get the same constant. I believe, so I haven't looked at their paper recently, but I believe
Would
that's,
imply very strong assumptions on their ergodic property.
yeah, maybe, I'd have to think about that statement a little bit. But certainly if you took a diffeomorphism homotopic to the identity and took that flow line, you would get the same constant.
Yeah, you're right.
Mapped it forward.
I think it does say
Perhaps we should look in different domains for higher helicities. You can find non-simply connected domains. You can find knotted flux tubes. You could find Brownian flux tubes, like this is a deformed region of the Borromean rings. And several people, starting with Monastirsky and several others in here, have been able to show that, well, if you take a set of Brownian flux tubes like we have there is a non-trivial third-order helicity, and it measures this Milnor mu bar invariant that Clay talked about, the mu 1, 2, 3 invariant. You know, and this is very intelligent work. There's a lot of currency to it. You're getting an invariant, but it's measuring the topology of the domain. It's reducing down to the topology of the thickened knots themselves. It's not really measuring the topology of the vector field. So in some ways, these are great results. In other ways, they're not the strength that we'd really like to get out. If you took the configuration space and maybe reordered the points or took some special subset of it, perhaps you could do something. And Jason and I believe we can recover something akin to the x and y integral formulations that Bott-Taubes had for the Vasiliev invariants. But again, this is measuring the topology of the tube, not the field. And for my penultimate slide, maybe we're being too geometric about things. Maybe asking for diffeomorphism invariants is kind of like looking for a way to get your groceries home from the store and asking for a race car. Maybe we should take something that's not geometrically as nice and the equivalent of a push cart, or I use a baby stroller to get my groceries home. Could we take a smaller set of diffeomorphisms, enforce some plasma flow conditions, some MHD conditions, and get something that's not a full diffeomorphism group invariant, but something that's a plasma flow invariant. And so Hornig and Yates were able to do this, and some interesting work that's coming out. So maybe that's the right approach for getting physically relevant flows. And so I'd love to hear what such constraints would be, and if we could see about putting those into a nice topological framework. I'll close with thanks and one parting question. If anyone knows of applications for where you need 2k plus 1 invariants, please let us know, because we have things that have that invariance. So thanks for listening, and thanks again to the New Institute.
Questions, please.
I just have a comment that the Butter and Marche result is only about facility invariance of knots. So really it's telling you there's no asymptotic knot invariants that are interesting, but it doesn't say anything about links.
Oh, that's a good point. So perhaps I overspoke there, but
I mean, well, anyway, it doesn't say that there aren't. I think it's certainly hard to come up with asymptotic link invariants, but I don't think it directly speaks to doing asymptotic link invariants.
so I see. My slides didn't overspeak because I said on there I said the Vassiliev invariant of knots. And we can show that this won't generalize for knots or links, but that's under very explicit circumstances of our construction.
So if we consider the closed tree manifold, so especially contact manifold, so we can get some good invariant like this situation.
So the generalization to manifolds it is a tricky one. It's certainly worth thinking about helicity there. I mean, my PhD thesis was on helicity on the three-sphere and domains inside the three-sphere, so I definitely like thinking about helicity on manifolds. In terms of what we've done, some of the constructions begin to fall back or fall down because, let's see, to go way back, you're not necessarily guaranteed on an arbitrary manifold that this lemma that I had, I need to go further back. Wow, I can't find it quickly. So the lemma that said a closed Dirichlet form was necessarily exact, that's not necessarily true on an arbitrary manifold. And certainly some people at Nair, for instance, have looked at Nair and Greist, have looked at helicity in a contact setting. And there's some interesting things to be said there. So maybe that's a suggestion for where to go. Maybe in the case of contact manifolds, one could come up with even more vector field invariants that may model helicity. But I don't know that anybody's been, well, I don't know if anything's come out lately on that.
Firstly, I'd like to say this talk is very interesting. Yeah, very inspiring. Yeah, thank you. And I have a question regarding the one formula you mentioned in your talk. That's a helicity based on differential form alpha. So that is a integral of alpha cross Biot-Savart of alpha. Yeah, just that.
One more.
Yes, yeah, this one. So my understanding for alpha is just so you said differential form is more elementary than vector field. So can I understand alpha as a velocity field? And Biot-Savart is just the vorticity.
That's right. And so that would be another formulation of this.
Yes. Okay. So totally, the integral is a triple integral.
That's right.
Biot-Savart is a double.
Yeah, that's right. This would be, well, there's an integral lurking in Biot-Savart here. And so if omega is a three-dimensional domain, this BS has another three-dimensional integral inside of it. So it's really kind of a six-dimensional domain or on two copies of the region. But there's no reason one couldn't think about this profitably in a velocity and vorticity sense for fluid flow. I don't know that I've had too many good thoughts in that direction, but it would be interesting to go further with.
And on the first formula, you have a G star volume. And so if you're talking about the C2 of omega or something, so it's easy to get that pullback of that because you just have two links. If you have C3, how to get that pullback?
Oh, that would be interesting. If you have 3 points, well, let me jump ahead one more to 4. If I had 4 points, what I could do is something like the x integral, where I would pair 2 of the points together and 2 more points together. And then I could map to 2 copies of the 2 sphere. And unfortunately, that was our conclusion that said, well, if you do this, all you're going to get out is a multiple of helicity squared. If you have 3 points, well, the Bott-Taubes construction that we were mimicking doesn't quite work well for odd numbers of points. But that's not to say you might not be able to find some good map to take a pullback under. For instance, the work that Clay talked about, they concocted this really nice pullback to recover a 3-term linkage. And so there's certainly ways to look at maps into 2 spheres and other objects that are analogous to this. But the overall construction doesn't push through with 3 points.
More questions? I have one. Can you show that picture with the 2 flux tubes that are square in shape and have square cross sections, the stapled dies of plasma physicists? And you said that it's enough to take the vertical vector and integrate, which effectively means that it's enough to take one chosen projection of that link and only do integrals around crossings.
That's right.
It seems to be a very strong statement, because that means that by simple integration that you can do on any computer, you can achieve the same as with all the combinatorial work, that you go around the link in identifying all the crossings and the linking number. And apparently what you're saying is that you can do that by trivial volume integral or surface integral.
Yeah, I don't, well, I guess my first response would be, yeah, gee, thanks. And my second response would be, I'm not quite sure that makes everything completely trivial, because you're still doing a 4-dimensional integral where you've got to, you do have to look at all points in the domain, but as you say, if you take a good projection where there's very little of the second flux tube crossing over the first.
Did you say a good projection? Oh, yes,
yeah.
but they would all...
Any projection would work.
The easiest.
Yeah, but
yeah,
if you take if you were to take a bad projection here, you may have lots of regions where the second tube is over the first. But if you were to take a nice suitable projection like we have here, there's only so many places where the second tube lies over the first tube. For instance, there's just this one crossing. And so we would really be restricting ourselves to this parallelogram to integrate over. Now we are assuming ideal flows. So we're assuming that the magnetic field is divergence free, is tangent to the
And you assume the same magnitude of the field everywhere, because
We did
otherwise you
here.
can get any number, I suppose, from that integral. I don't know.
just like you can get any number for Helicity,
Yes.
right? So if
Yes.
it-
So how do you take the norm of that?
well, no, I mean, it still works. The formula still works for any field. The point is that you'll get like flux times linking number, right? Just as the
Right.
everything predicts. Right? It's sort of parallel to computing the length for two curves, either by doing the Gauss linking integral, which is a two-dimensional integral, or by summing signs of crossings, which is, you know, a sort of combinatorial, you know, zero-dimensional integral, if you like. This is kind of exactly parallel, right? You can get Helicity either by doing the six-dimensional Helicity integral, or by doing the two-dimension lower four-dimensional integral,
Yes.
you know, which is sort of the equivalent of the combinatorial form.
This may be more labor intensive, but at least I would know how to write an algorithm for that integral. I wouldn't know how to write an algorithm for crossings counting.
Ah, okay, yeah, sure. This is right. This is easier to write in that sense. Yeah.
But you can just put in delta functions, right, in your integral, so it turns into an integral.
Yeah, numerically they are awkward delta functions.
So, well, yeah.
Yeah, so our hope with this was that it really would diminish the computational prowess taken to compute Helicity. And as Jason says, well, I mean, the reason it's working is we can't just say, oh, over here, we're going to all of a sudden stop having fluxes because, well, under ideal flow, the flux is going to be constant over any two homologous flux surfaces. But yeah, you could get lots of different things out. I'd love to find out if it's actually computationally helpful to anybody.
Well, I don't know about you, but all that makes me hungry.